Okay, dot product and projection. Okay, what's dot product have to do with projection? Example, we're going to project v equals 3, 1 onto w equals 2, negative 1. Okay, we've got a picture of v and w here. Relatively accurate picture. I'm not sure my scale's all that consistent. And what we want to do is project v down onto the line of w. So we project down here, and let's just say it comes down about here. So that the projection of v on w is this vector here. Now that vector is pretty close to the v vector. So close I can't really tell from the sketch which side of the v vector is it on. Is it actually a little longer in the v vector the way I drew it here? Or is it maybe a little bit shorter? I can't tell. Can't tell. Okay, because my picture isn't accurate enough. In any case, the magnitude of the projection is the magnitude of v times the absolute value of the cosine of theta. Now I wrote v cosine theta a little close, so let me rewrite this. Okay, it's the magnitude of v times the magnitude of cosine theta, as we've seen previously. Okay, well, we know from what we saw before that v dot w is magnitude of v times magnitude of w times cosine theta. And look what we've got here. We've got the magnitude of v times the cosine of theta right here. So the magnitude of v times cosine theta is just what we get when we divide out this magnitude of w. It's going to be v dot w over magnitude of w. Now let's write this out. Since this is true, the magnitude of v times the cosine of theta equals v dot w divided by the magnitude of w. And if we want the magnitude of v times, or the magnitude of the projection, the magnitude of v times the absolute value of the cosine of theta, we just put absolute values around this side and we'd have it. I'm going to leave it the way it is for a moment. Okay, so the magnitude of the projection is then v dot w over the magnitude of w. Okay, what are we going to do with that? How are we going to get the direction of this? Well, I'm going to pull out a little magic here and say that, okay, well, let's see. Okay, this need absolute value signs around this because v dot w can in many cases be negative. There's no reason v dot w couldn't be negative. You multiply a row by a column, you get a positive or a negative depending on what the v and the w are. Okay. I'm going to wave my hands a little bit right here and say, first of all, need a statement. If we divide W by the magnitude of W, that's like dividing a vector by its length, we don't change the direction of W, but we do change its magnitude. If we divide a vector of length 5 by its length, we get a vector of length 1. Whatever the length of W is, if we divide it by the magnitude of W, we have a vector of length 1. So, I'm going to say then that W divided by its magnitude is W divided by its length, so it's a vector of length 1. Okay. Then W over magnitude of W is in the same direction as W. If you divide or multiply a vector by a positive number, you don't change its direction. If you multiply by a negative number, well, you don't change the line of its direction, but you reverse its direction. But the line that the vector describes is still the same. Okay, so W over magnitude of W is in the same direction as W. Okay, it follows that I don't have room to write out all the details of the argument. This is most of them. I'll put a few dots here. There are a few things to be filled in, but I can say that if we multiply this vector, this unit vector, this vector of length 1 by this quantity v dot W over magnitude of W, we get a vector in the direction of W whose magnitude is that of the projection. Okay? Again, the magnitude of the projection is the magnitude of V times the magnitude of sine theta, cosine theta. Magnitude of V times cosine theta is V dot W over magnitude of W. So here we have something whose magnitude is the magnitude of the projection multiplied by a vector in the direction of W. Well, the projection is in the direction of W. So that V dot W over magnitude of W times W over magnitude of W is a vector of length equal to the projection of V onto W in the direction of the vector W. There's a little more to it. Remember, this thing could be negative. Okay, well, if it's negative, that's okay, because if you multiply this by this and this is negative, that means it's in the opposite direction on W. Now, I'm not going to get into all the detail of that. We'll do that argument more thoroughly later on. But this has a direction of W or its opposite. That is, the direction of W or the direction opposite W. and magnitude of the projection so this is the projection. Okay, so I'm going to kind of write that out here. So this thing here, I'm going to fill in the only space I have left on the board and say that the projection onto W of V equals V dot W over the magnitude of W multiplied by the unit vector W over magnitude of W. In this case, and I'm looking for room to do this now, in this case, V dot W is 5. Magnitude of W is the square root of 5. W is a vector 2, negative 1. Magnitude of W is the square root of 5. So how about that? No wonder I had trouble figuring out whether this projection was here or here. The projection is just the vector W. Now I did that calculation in my head. I'm going to go on in the next video and run this calculation and see. And that's just a totally off the wall coincidence. I just made up these vectors. Okay. I didn't have any objective in mind other than to get a couple of vectors that I could easily label, and proceeded and find that this vector is the projection of this, which means my figure was pretty accurate, since I couldn't really decide whether I was cheating to the right or left by drawing the projection line here. Okay, well, miracles occur, and there's another one. Okay, not sure whether it's a good miracle or a bad miracle, but it's kind of a miracle. Okay, that's kind of a complicated argument. It comes down to this. Do try to understand what we've learned about the dot product, why the magnitude of this is this, and then why multiplying this magnitude of V cosine theta by the unit vector W over magnitude of W gives us our vector projection.